This is a video from section 16.2. The directions say to evaluate the line integral where C is the given space curve. We're going to take a look at number 9. We're going to take the integral over C of x squared y ds. And C is given by the parametric equations x equals cosine t, y equals sine t, z equals t, and t is less than or equal to pi over 2 and greater than or equal to 0. Okay, now what I want to do is I want to find ds. Well, to find ds, I need to find dx dt, which is negative sine t, dy dt, which is equal to cosine t, and dz dt, which is equal to 1. And so ds is the square root of dx dt squared, which is negative sine t quantity squared, plus dy dt squared, which is cosine t quantity squared, plus dz dt squared, which is 1 squared dt. But remember that sine squared t plus cosine squared t is equal to 1. And so that says ds is the square root of 2 dt. And so therefore, the integral over c of x squared y ds is equal to the integral from 0 to pi over 2. Now, x is cosine t. So I'm going to take cosine t and square it. Y is sine t. And then my ds is square root of 2 dt. So again, this is all substitution all the time, right? And so I'm going to pull the square root of 2 out in front, and I'm going to take the integral from 0 to pi over 2 of cosine squared t times sine of t dt. And if you guys are comfortable doing this without a u substitution, what you should come up with is the following. It'll be square root of 2 times negative 1/3 cosine cubed t evaluated from 0 to pi over 2. If I plug pi over 2 in for t, remember that cosine of pi over 2 is equal to 0. So this is square root of 2 times, essentially you're going to get 0 minus negative 1/3 cosine cubed of 0. And so the answer here is square root of 2 over 3. Why? Because remember, cosine of 0 is equal to 1. And so hence that's what you get for number 9. If we take a look at another one, so I'm going to take a look at number 12. Suppose I had the integral over c of x squared plus y squared plus z squared ds. And c is the curve described by the parametric equations x equal t, y equal cosine 2t, and z equals sine 2t. And t is between 0 and 2 pi, like so. Well, dx dt is equal to 1. dy dt, by the chain rule, you guys, is negative 2 sine 2t, and dz dt is 2 cosine 2t. And so that's going to allow me to get ds. That's the square root of 1 plus negative 2 sine of 2t to the second plus 2 cosine 2t to the second. This whole thing dt. So remember, I'm taking the square root of dx dt squared plus dy dt squared plus dz dt squared dt. So ds, you're finding that piece of arc length. And so here, ds is the square root of 1 plus 4 sine squared of 2t plus 4 cosine squared of 2t. And then, again, that's dt. If I factor out a 4, notice I get sine squared t plus cosine squared t, which is equal to 1, right? And so that says that ds is square root of 5 dt. And I'm in business because now I get the integral over c of x squared plus y squared plus z squared ds. And that's square root of 5. I'm just going to pull that to the outside of the integral. I'm going to integrate from 0 to 2 pi. X is equal to t. So I get t squared. Y is equal to cosine 2t. So I get cosine squared of 2t. Z is sine squared 2t. And then I'm integrating with respect to t. I hope you guys can see that okay. You need to have dt there, right? Now, this is square root of 5 times the integral from 0 to 1 of t squared plus 1 dt, right? Because cosine squared of 2t plus sine squared of 2t is equal to 1. And so that's square root of 5 times 1/3 t to the third plus t, evaluated from 0 to 1. And so the answer here is square root of 5. If I replace t with 1, I get 4/3. So again, the answer to this is number 12, is 4 square root of 5 divided by 3. And if I take a look at number 13, suppose I have the integral over c of x, y, e to the yz dy. So this one's a little bit different, but the principle is the same. Now, c is the curve described by the following. You get x equals t, y equals t squared, and z equals t cubed. And t is between 0 and 1. Now, when we go to make our substitution, we got to just really watch what we need, right? So in this problem, the integral over c of x, y, e to the yz dy is the integral from 0 to 1. X is t. Y is t squared, right? E to the yz, which is t squared times t to the third times dy is 2t dt. So I'm going to write 2t dt. So this is the integral from 0 to 1. T squared times t is t cubed. T cubed times t is t to the fourth. So I get 2t to the fourth e to the t to the fifth dt. So this is the integral from 0 to 1 of 2t to the fourth e to the t to the fifth dt. And so u is t to the fifth, du is 5t to the fourth dt. So if I solve for t to the fourth dt, I get 1/5 du. And I'm going to pull the 2 out as well, so I get 2/5, the integral. Now, when t is 0, u is 0. When t is 1, u is 1. And so I'm going to integrate from 0 to 1 of e to the u du, which is 2/5 times e to the u, evaluated from 0 to 1. And so the answer here to problem 13 is 2/5 times e minus 1. Because remember, e to the 0 is 1. And that's how number 13 works. Well, let's do another one. We'll take a look at number 14. Suppose I had the integral over c of y(e) to the z dz plus x ln x dy minus y dx. And c is described by the following parametric equations. We have x equals e to the t, y equals 2t, and z equals natural log of t. And t is less than or equal to 2 and greater than or equal to 1. Now, again, this is all substitution all the time. And so remember, t goes from 1 to 2. Now, dx is e to the t dt, okay? dy is 2 dt, and dz is equal to 1 over t dt. It's just like you do in Calc 1, okay? Now, y is 2t, so I'm going to put a 2t here. Z is natural log of t, so I have 2t e to the natural log of t. dz is 1 over t, and then I'm going to save the dt for the end, okay? So I'm going to go plus x, which is e to the t, natural log of e to the t, dy is 2 dt. So I'm going to go times 2. Minus 2t. And then dx is e to the t dt. So I put the dt on the end. Now, let's go ahead and simplify this a little bit. So we're going to take the integral from 1 to 2 of t's cancel. So I get 2t plus, now natural log of e to the t is t. So I get 2t e to the t minus 2t e to the t dt. So this simplifies really nicely because notice how these terms cancel. And so we're just integrating from 1 to 2 of 2t dt. Let's double check, and it's just that first term. Oh, let's go back. And so this is t squared, evaluated from 1 to 2, which is 4 minus 1, which is equal to 3. Remember, 2 squared is 4, 1 squared is 1. And by the fundamental theorem of calculus, you got to subtract those. And that was number 14. So let's do one more for this video, and then we'll do a couple of different ones in the next video. So if we take a look at 15, suppose we have the integral over c of z dx plus xy dy plus y squared dz. Now, c is described by the parametric equations x equals sine t, y equals cosine t, and z equals tangent t. And remember, t is less than or equal to pi over 4 and greater than or equal to negative pi over 4. Now, dx, right? Because we're going to need dx, we're going to need dy, and we're going to need dz. So let's get them. dx is cosine t dt. dy is negative sine t dt. And dz is secant squared t, right? The derivative of tangent t is secant squared t. And we're in differential notation, so we got to just attach that dt. So if I take the integral over c of, let's go back, z dx plus xy dy plus y squared dz. Now, this is the integral from negative pi over 4 to pi over 4. Now, z is tangent t. So I'm going to put a tangent t here. dx is cosine t dt. But remember that we saved the dt for the very end. So I'm going to write times cosine t plus x is sine t. Y is cosine t. dy, let's go back, is negative sine t. So I'm going to write negative sine t plus, now y is cosine t. So I have cosine squared t. dz is secant squared t. And this whole thing is being integrated with respect to t, which I hope you guys can see here. Now, cosine squared t times secant squared t is equal to 1. Why? Because remember, secant squared t is 1 over cosine squared t. Okay? Now, this, again, is the integral from negative pi over 4 to pi over 4 of. Now, I'm going to take sine t divided by cosine t, that's just tangent t, times cosine t, minus cosine t times sine squared t plus 1 dt. This probably looks a little nastier than what it is, okay? Because now watch what happens. The cosine t's go away, and what you end up getting is the following. This is the integral from negative pi over 4 to pi over 4 of. I get sine t minus cosine t times sine squared t plus 1 dt. So if I go through the integral, I get negative cosine t. So remember, I'm thinking of the function whose derivative is sine t. Okay? And then I'm going to go minus 1/3 sine cubed t plus t evaluated from negative pi over 4 to pi over 4. So if I replace t with pi over 4, I get negative square root of 2 over 2. And then I'm going to subtract a third times square root of 2 over 2 to the third plus pi over 4, okay? And then I'm going to plug in negative pi over 4. But cosine of negative pi over 4 is square root of 2 over 2. So I get negative square root of 2 over 2. And then sine of negative pi over 4 is negative square root of 2 over 2. Okay? So I'm going to get minus a third times negative square root of 2 over 2 to the third minus pi over 4. Now, pi over 4 minus a negative pi over 4 is pi over 2. And then negative square root of 2 over 2 plus square root of 2 over 2, these terms cancel. And then I get minus a third times 2 root 2 over 8. And then a negative times a negative is a positive, and there's another negative there. So I'm going to get minus a third times 2 root 2 over 8. And so if I go a little bit further than that, I'm going to get the following. I'm going to get pi over 2 minus 2/3 times, and then I get 2 root 2 over 8. And so I get pi over 2 minus root 2 over 6. Your instructor might want you to get a common denominator, and if that's the case, you can write it as 3 pi minus square root of 2 over 6. So it depends on what your instructor is looking for. And that's going to conclude this video for section 16.2. We worked on problems 9 and then 12 through 15. Thank you.